Join me as I dive into the mind-bending world of quantum tunneling and challenge myself to explain its incredible science and technology blend in just 5 minutes. Quantum tunneling is a fundamental concept in physics that has significant implications in both science and technology, allowing particles to pass through barriers that are theoretically too high for them to overcome. Particles don't behave like we'd expect them to, and this is where misconceptions about their behavior come into play. Scientists face challenges when explaining quantum tunneling because it seems to defy classical logic, making it difficult for people to wrap their heads around the idea that particles can be in two places at once or tunnel through solid objects. The Heisenberg uncertainty principle plays a huge role in understanding quantum tunneling, as it states that certain properties of particles, like position and momentum, can't be precisely known at the same time. This principle contributes to the mystique surrounding quantum mechanics and makes it even harder to comprehend how particles can tunnel through barriers. Misconceptions about quantum tunneling often arise from trying to apply classical physics to a quantum world, which just doesn't work. The rules of classical physics are intuitive and based on everyday experience, but quantum mechanics operates on a completely different level, where the principles of wave-particle duality and superposition come into play. Understanding the behavior of particles at the quantum level is crucial for advancing various fields, including electronics and medicine. Quantum tunneling has been observed in numerous systems, from scanning tunneling microscopes to certain types of transistors, and its implications are vast, enabling the creation of smaller, faster, and more efficient devices. Quantum tunneling works by allowing particles to pass through potential energy barriers, which is made possible by the wave-like nature of particles. This phenomenon has significant implications in fields like electronics, where it's used to create ultra-small devices, and medicine, where it's being explored for its potential in drug delivery and imaging techniques. The applications of quantum tunneling are vast and varied, from quantum computing to medical imaging. In quantum computing, quantum tunneling is used to create quantum bits or qubits, which are the fundamental units of quantum information. In medical imaging, quantum tunneling is being explored for its potential to create ultra-high-resolution images of the body. Groundbreaking technologies like tunneling microscopes and quantum computers rely heavily on quantum tunneling. These technologies have the potential to revolutionize numerous fields, from materials science to cryptography, by enabling the creation of new materials, simulating complex systems, and developing unbreakable codes. Quantum tunneling has led to the development of innovative technologies, including flash memory and certain types of diodes. These technologies have transformed the way we live and work, enabling the creation of smaller, faster, and more efficient devices that are used in a wide range of applications, from consumer electronics to industrial systems. The impact of quantum tunneling on modern science is immense, with potential applications in fields like energy and transportation. Quantum tunneling could be used to create more efficient solar cells, fuel cells, and batteries, which would have a significant impact on the way we generate and consume energy. In conclusion, quantum tunneling is a fascinating phenomenon that has significant implications in both theoretical and practical contexts. Its importance in advancing our understanding of the quantum world and developing new technologies cannot be overstated, and continued research into this phenomenon is crucial for unlocking its full potential. If you've made it this far, be sure to leave your thoughts in the comments and check out another video on related scientific phenomena, where we'll delve into the mysteries of black holes and dark matter.